Welcome back, friends. In this video, we're going to talk about the vector considered with its parametric equations for ideal projectile motion. So when we talk about ideal projectile motion, we're talking about leaving from the origin with no interfering additional factors. A classic example of integrating vector functions is this derivation of the equations for motion of a projectile. Now, we're not going to specifically derive all of the equations, but I'm going to talk a little bit about how they have come to be. When we talk about projectile motion from a physics standpoint, what that means is we're describing how an object fired from some angle at an initial position, acted on only by the force of gravity, moves in a vertical coordinate plane. In the classic example, we always make sure we ignore these effects of any frictional drag on the object, which may vary with speed and altitude. And we also ignore the fact that the force of gravity changes slightly with the projectile's changing height. As you get higher, that effect of gravity is a little less. In addition, we ignore the long distance effects of the Earth turning beneath the projectile, such as a rocket launch or the firing of a projectile of the cannon. So ignoring these gives us this ideal projectile motion. It's a reasonable approximation for the motion in most cases. So let's just look at the components and kind of what this looks like. I'm going to pull in a picture. So we're looking at a projectile, and the projectile is traveling along this blue path. We have some V naught or V sub 0, and V naught is the velocity vector. And so as the projectile moves, obviously that velocity vector can change. As we reach that peak before we start returning to Earth, the velocity vector is going to slow down, reach 0, and then we'll start our descent. Now, one thing we know, the magnitude of the velocity vector, we'll call that V naught, without vector notation above it, is speed. So we have speed here. And V naught, our velocity vector here, can be written in component form. So we have that component, the speed, times a horizontal component, cosine of alpha I, we should put magnitude there, plus the speed, the magnitude of the velocity, times the vertical component, we use sine of alpha j. The initial position, my r vector, and we'll say that initial position, I'll call it r naught, is the 0 vector. So we're starting at the origin. I have 0i plus 0j, or rather, do bold 0, or we put that vector notation above it. So you see the horizontal and vertical components of velocity, some launch angle alpha, and then our initial starting position at t equals 0. And then you see this A going straight down. So I'm going to talk a little bit about where that A comes from. A is the vector that is developed from acceleration due to gravity. Hopefully you have at least heard of Newton's second law. And Newton's second law tells us that force equals some constant mass times acceleration. So we're going to assume three things. One, that mass remains constant. Two, the only force acting on an object after launch is gravity. This is what partially makes it ideal. And that three, gravity is a constant since we're close enough to Earth, right? As you get much further into the atmosphere, the gravity changes, but we're not going far enough away, so gravity is going to remain constant. So if we consider that, so let's think about what that mass times our acceleration vector looks like. Well, we have a mass times some downward gravitational force times a vertical position vector, this J vector. And if we divide by mass on both sides, we have that A equals negative G times the vector J. So if we now have this acceleration, one thing we know is that velocity is the integral of acceleration, or rather the integral of negative G J dt. Integrating this, we would get negative gt times the vector j plus some c sub 1. And we use initial conditions here. We say at t equals 0 that my v of 0 equals v naught, or rather we have an initial velocity of v naught. So doing some calculations, we can determine that this c sub 1 is equal to whatever the initial velocity is. So we can determine here that our v vector equals negative gt times j plus v naught. Further expanding, what we know is that my r vector is going to be the integral of my v vector, right? The first derivative of position is velocity, therefore the integral of velocity will give us position. So my velocity vector here is really the derivative of position r with respect to t. And with a quick similar integration and using an initial value, we've got 1/2 gt squared times my j vector plus v naught t plus some c sub 1 value, again using initial positions, or rather I should say initial values. We get some r naught here. So now remember, from our initial definitions, from what we originally defined, we know what this v naught, and that v should be a vector. Let me fix that. But we know what the v naught and the r naught are. So if we sub those in from what we initially started with, we've now, with, some brief thought here, derived our position vector. And it's always going to be negative 1/2 gt squared combined with vertical motion plus, I have v naught cosine alpha, that horizontal component of velocity, t times I, plus v naught sine alpha, the vertical component of velocity, t j, plus some zero vector. And with a little bit of manipulation, we have our ideal projectile motion equation, right? So looking at this equation, alpha refers to the launch angle or the angle of elevation. And then this v naught, the magnitude of our velocity vector, is the initial speed. So let me write that in there. We've got that alpha is the launch angle, or our angle of elevation, and then the magnitude of the v vector gives us this v naught, which is an initial speed. And you'll notice we have these two components here. So these are our parametric equations. So we see that v naught cosine alpha t, that's giving us x being the distance downrange. And v naught sine alpha t minus 1/2 gt squared, That's representing the height of the projectile at any time, and both of these are at any time t after greater than equal to, I should say, 0 after launch. Couple things to keep in mind. Ideal projectiles move along parabolas, and that highest point, that maximum, is when the vertical velocity component is going to be equal to 0, right? Because there's no velocity right at the max. You're going up, you slow down, you come to a stop, and then you change to your downward motion. So now let's do an example. For this example, we're going to example a projectile fired from the origin over horizontal ground with an initial speed of 500 meters per second and a launch angle of 60 degrees. Where will the projectile be 10 seconds later? All right, so we have a couple of things to unpack. First of all, we have an initial speed, v naught, and that is 500 meters per second. We have a launch angle, alpha, 60 degrees. Now, because we are dealing with a metric system, we have a value that we use for g, and it's 9.8 meters per second squared. So this is our metric acceleration due to gravity. And then we also know that we're going to be solving this problem or looking at t equal to 10 seconds. As a note for this g, if we were in the imperial system using feet or yards, we use 32.1 feet per second squared. So just keep that in mind when you're working through some of these problems. You may have to know that. All right, well, as we just defined, we said that our r of t vector is the speed times cosine of that launch angle times time t times your vector I plus v naught sine alpha t minus 1/2 gt squared. And that would be times your vector j. So we're just going to plug our values in. We know what our v naughts are. I know what my alphas are. I know what g is, and then I know what my t values are. So my position is going to be, let's see, I've got 500 cosine 60 times 10 I plus 500 sine of 60 times 10 minus 1/2 9.8 times 10 squared j. Simplifying, cosine of 60 is 1/2, so 500 times 1/2 is 250 times 10. I have 2500 I plus 500 sine of 60, that's root 3 over 2, so that's going to be 250 root 3, times 10 would be 2500 root 3, minus 9.8 divided by half, that's 4.9 times 100, so that would be minus 490 j. Or if we approximate that, we'll have roughly 2500 I, and the decimal value for 2500 root 3 minus 49 will be plus 3840 j. And I'm noticing one thing when I plugged in that 10, these t's here, these should have turned into r of 10. So what this says is that the position 10 seconds after launch. We are 2,500 meters downrange from origin at a height of 3,840 meters in the air. So 2,500 meters is the distance downrange, and 3,840 meters is the current height, H-E-I-G-H-T. So, just keep in mind this was ideal projectile motion, meaning no outside forces other than the effect of gravity because we're close enough to the surface of the Earth. And we're starting at the origin. So we do have some other formulas that can help us with ideal projectile motion. So we have height, flight time, and range pulled in here. I don't think you need to memorize these. They can be derived relatively easy and they're in your text. But they're useful to know that we do have some formulas for them. So for the ideal projectile motion, we can find a maximum height by taking that vertical component, squaring it, and dividing by 2 times that gravitational force. Flight time, 2 times the vertical component divided by gravity. And then the range, the speed squared divided by gravity times the sine of 2 of that launch angle, doubling the launch angle. And I bring these 3 pieces in here merely because you may be asked about them in your homework. So one more thing, ideal projectile motion means we're starting at the origin and we are limiting any of these outside factors that could affect the motion of our projectile. But not all projectiles start at the origin. So I'm going to pull one more formula in. So in our last problem that we talked about, we started or initiated at the origin. However, if we are not starting at the origin, x naught, y naught, then we're going to include that x naught, y naught in our calculation, in our horizontal and vertical component pieces. And so it's just as simple as adding those 2 factors in there. And again, you may see this in your homework. All right, so we have one more video in our series. I'm going to cover that next.